Imagine a world where you could command sound itself, a world where you could sculpt silence as easily as a potter shapes clay. This isn't science fiction, it's the dawn of a new scientific revolution, powered by something truly extraordinary: acoustic metamaterials. These aren't materials you dig out of the ground, they are materials designed and engineered with intricate, repeating structures, smaller than the wavelength of the sound they are meant to control. Their power doesn't come from their chemical composition, but from their physical form. It's their geometry, their very architecture, that grants them almost magical abilities to manipulate sound waves in ways that were once thought impossible. Think of it this way: a normal material, like a concrete wall, absorbs or reflects sound based on what it's made of. It's a blunt instrument. But an acoustic metamaterial is like a sophisticated orchestra conductor. It can bend sound around an object, making it seem to disappear, creating a cloak of silence. It can focus sound into a tiny, powerful point, like a sonic magnifying glass. These materials are built from an array of tiny resonators. Think of them as miniature tuning forks, all working together. By carefully arranging these tiny structures, scientists can dictate exactly how sound travels through them, unlocking a whole new rulebook for acoustics. This ability to precisely control sound waves opens up a universe of possibilities that extends far beyond just making things quiet. It's about fundamentally changing our relationship with the physical world of vibrations. We are moving from being passive observers of sound to active architects of our sonic environment. The principles that govern these materials are universal, applying to all kinds of waves, from the gentle lapping of water to the violent tremors of an earthquake. This is more than just an incremental improvement in technology, it's a paradigm shift, a new way of thinking about how we can engineer our world, one vibration at a time. The journey into this new frontier is just beginning, and the destinations are more fantastic than we can fully comprehend. For centuries, we've built walls to block noise. Now we're designing materials that can guide sound on a specific path, filter out unwanted frequencies with surgical precision, or even make sound behave in non-intuitive ways. The cosmos is filled with waves, from the light of distant stars to the gravitational ripples of black hole collisions. Here on Earth, by mastering the waves of sound, we are taking a monumental step toward becoming masters of our own physical reality. The symphony of the future is being composed right now, and its instruments are these remarkable, intelligently designed materials. Now, let's take a step deeper into this rabbit hole. What if a material could change its properties on command? This is the realm of nonlinear acoustic metamaterials. Unlike their simpler cousins, which have a fixed structure, these materials can respond and adapt to the sound passing through them. Imagine an umbrella. It has a simple, compact form when closed, but with a small push, it expands into a completely different shape, ready to block the rain. Reconfigurable metamaterials work on a similar principle. They can be designed to shift their internal geometry when a certain condition is met, like a change in pressure, temperature, or even the intensity of the sound wave itself. This non-linearity unlocks a whole new level of control. A material could be programmed to block low-frequency rumbles but allow high-frequency sounds to pass through, and then switch those properties in an instant. It's like having a set of sonic instructions embedded directly into the material. This leads to exciting ideas like acoustic switches that can turn sound transmission on or off, or harmonic generators that take a simple tone and transform it into a rich, complex chord by creating new frequencies. This is not just filtering sound, it's actively reshaping it, creating an interactive sonic experience that depends on the sound itself. Then there's an even more mind-bending concept: non-reciprocal devices. In our everyday experience, sound is a two-way street. If you can hear me, I can hear you. This principle is called reciprocity. But what if we could break that rule? What if we could build a device that lets sound travel from point A to point B, but completely blocks it from traveling back from B to A. This is precisely what non-reciprocal acoustic metamaterials do. They create a one-way path for sound. It's the acoustic equivalent of a one-way mirror, letting you hear what's happening in the next room without them hearing you. Achieving this requires some clever physics, often involving circulating fluids or spinning components within the metamaterial's structure to break the symmetry of wave travel. The implications are staggering. This technology could lead to the ultimate noise-cancelling headphones, which don't just absorb sound, but actively prevent it from ever reaching your ears. It could revolutionize ultrasound imaging by eliminating the echoes that cloud the picture, giving doctors a much clearer view inside the human body. We are essentially teaching sound to obey traffic laws, telling it where it can and cannot go. And in doing so, we're paving the way for technologies that were previously confined to the realm of pure imagination. The power of metamaterials extends beyond the sound we can hear. It encompasses all forms of mechanical vibrations, from the tiniest tremors in a machine to the cataclysmic shaking of an earthquake. This is where elastic and mechanical metamaterials come into play. They are designed to control the propagation of these physical waves through solid objects. Imagine a forest. When the wind blows, each tree sways, absorbing and scattering the wind's energy. An elastic metamaterial works in a similar way, but on a much more sophisticated scale. It can be designed to create band gaps, specific frequency ranges of vibrations that are forbidden from traveling through the structure. Think of it as a fortress for vibrations. If you build a building on a foundation made of these metamaterials, you could potentially design it to block the specific frequencies of seismic waves generated by an earthquake. The ground would shake violently all around the building, but the structure itself would remain eerily still, protected by an invisible shield that deflects the destructive energy. This isn't about making the building stronger in the traditional sense. It's about making it invisible to the earthquake's vibrations. The same principle could be applied to protect sensitive laboratory equipment from minute vibrations or to silence the drone of a ship's engine. Now let's look at the universe for inspiration. A material called graphene, a single layer of carbon atoms arranged in a honeycomb lattice, has shown us how much power can be packed into a two-dimensional structure. Inspired by this, scientists are now creating graphene-inspired acoustic metamaterials. These are ultra-thin, lightweight sheets patterned with a similar honeycomb design. They possess bizarre and wonderful wave-guiding properties. Sound waves traveling through them can behave in strange ways, following the edges of the material without scattering or being topologically protected, meaning the wave will continue on its path even if the material has defects or imperfections. This robustness is a game changer. It means we can create acoustic circuits that are incredibly efficient and resilient, similar to how electrons flow through a copper wire. We could channel sound energy with pinpoint accuracy across a surface, creating new types of sensors or communication devices. Furthermore, we are exploring non-Hermitian systems, a concept borrowed from quantum physics. These systems strategically introduce energy loss or gain into the material. By carefully controlling where sound energy is absorbed, or loss, or amplified, which is gain, we can achieve even more exotic effects, like creating a device that perfectly absorbs any sound that hits it from any direction, a true black hole for sound. So, where is this grand journey taking us? The convergence of these new directions, nonlinear, non-reciprocal, elastic, and bio-inspired, is not just an academic exercise. It is charting a course toward a future where we have an unprecedented level of control over our physical environment. The potential applications are as vast as the cosmos itself. In medicine, we can imagine hyper-focused ultrasound that can destroy tumors deep within the body without harming the surrounding tissue, or advanced imaging systems that provide crystal-clear, real-time views of our internal biology. It's a future where surgery could become less invasive and diagnostics more precise. In our daily lives, the impact will be just as profound. Imagine cities where the roar of traffic is silenced not by heavy concrete barriers, but by lightweight, transparent materials lining our highways and windows. Picture concert halls where the acoustics can be digitally tuned in real time to perfectly suit a solo pianist one moment and a full orchestra the next. Or consider homes where you can create zones of perfect silence with the push of a button, finally ending the battle over the television volume. These materials promise a future that is not only quieter but also more personalized and responsive to our needs. The dream of protecting our infrastructure from the awesome power of nature is also moving closer to reality. The concept of shielding entire buildings, bridges, and power plants from earthquakes is a monumental goal that could save countless lives and prevent trillions of dollars in damage. By embedding these metamaterial structures into the very foundations of our civilization, we can build a world that is more resilient, more secure, and better prepared for the planet's unpredictable forces. This is engineering on a cosmic scale, using the fundamental laws of physics to protect and improve human life. We stand at a precipice, gazing into a future sculpted by these incredible materials. What started as a theoretical curiosity is rapidly becoming a powerful tool for innovation. From the quietest whisper to the most violent tremor, we are learning the language of waves, and with that knowledge we are becoming the authors of a new reality. The quest to understand and control our world is a deeply human endeavor, one that connects us to the great explorers and scientists of the past. With acoustic metamaterials, we are not just building better devices, we are composing the silent, resilient, and wondrous symphony of the future. The universe is waiting.